But first of all, I would like to talk about Fluxgate Magnetometers itself. So you're kind of familiar, I hope, with the Fluxgate Magnetometer principle, but just a short introduction at the beginning. So Fluxgate magnetometers measure the magnitude and direction of a DC or low frequency magnetic field. And the second point here, gain knowledge of planets. That's what the scientific stuff basically does with the data provided from the front end. So I'm not going to talk in detail about this because I don't have knowledge here. However, Fluxgate magnetometers of a high dynamic range can achieve a low noise performance. And this performance or parameters are achieved by a dedicated front-end electronic circuitry. So the Fluxgate sensor requires dedicated front-end electronic circuitry to assure accurate measurements. So here on the right-hand side, for example, you can see a Fluxgate sensor. And on top, for example, this is the photograph of the Finnish Cube satellite. It's the 4-cell-1 satellite in this case. So how to measure the magnetic field? I would go in detail because this is a very, very important slide to understand the system. So the Fluxgate sensor itself consists of a soft magnetic ring core and has different windings for excitation, for sensing. And the first step is that the ring core must be periodically driven into saturation. And this is typically done by a circuit called here excitation circuit. And this circuit drives the magnetic ring core into saturation at the fundamental frequency called here F0. So if there's an external magnetic field present, then there will be a voltage induced in the sense winding, which is not shown here, but you can imagine that in this block there is a sense winding. This voltage contains the magnetic field information. And I have to say that the information is stored at the even harmonics of this fundamental excitation frequency. However, there are also odd order harmonics that couple from this excitation to the sense winding. The next block then here is the readout circuit that must extract this magnetic field information. This is typically done by an amplifier, a filter, and an analog-to-digital converter. So what does this circuit? Amplifies the input voltage, and then because the magnetic field information is stored at twice the frequency of the excitation frequency, the circuit must demodulate the field back to DC because the Fluxgate magnetometer is basically a DC instrument. And then an analog to digital converter transfers this analog information into the digital domain. The next building block then is or can be implemented on an FPGA, for example. It basically, it's an integrator and provides a feedback signal for the feedback circuit. So as you can see, it's a closed loop system. And this feedback circuit provides a current for the feedback coil, which is not shown here in the Fluxgate sensor, but you can imagine it. And the feedback circuit consists of a digital to analog converter, because we are coming from the digital domain. So this digital to analog converter then has to provide a specific current for the feedback coil to cancel the ambient magnetic field. And by doing this, you extend the linearity of the measurement. So here are some prior art space qualified front ends. On the left-hand side, you can see a big PCB where a lot of discrete components are, and an FPGA. An FPGA stands for a field programmable gate array, and it's a kind of circuit that houses digital components or digital circuitry. And on the other hand, here in this red box, you can see an application-specific integrated circuit, short for ASIC. And in this case, it's the well-known magnetometer frontend from the frontend group, for the magnetometer group. So what is clearly evident when you have looked at those two pictures, that the integrated front end offers a quite good, how could I say, the discrete components and the FPGA uses much more space as compared to the integrated version. And of course, when it comes to integrated front ends, they offer a much reduced power consumption. And there is another benefit, which I would say is when it comes to space qualification. Because when you have the all the required functionality on a single chip, you just have to qualify one single system and not worry about the qualification of individual components. However, the integrated front ends lack when it comes to the achieved noise performance and the magnitude that can be, or the magnetic field magnitude that can be measured in space. So, but first of all, I would like to give a short introduction in integrated circuit design. So what I would like to show here on this slide is a short comparison between integrated circuit design and when you design circuit using discrete components. First of all, the main difference is that when it comes to discrete circuit design, we basically need a printed circuit board where you place your individual components. However, when it comes to integrated circuit design, there's one major issue when it comes to the components that are available, is that for integrated circuits, that we have basically 3 or maybe 4 devices: resistors, R, capacitors, which is denoted here as C, then transistors, and a diode. However, when you compare it to discrete components, you can buy, for example, digital to analog converters or analog to digital converters, inductors, and stuff like that. The advantage of this is they have very defined parameters. You get the data sheet, and you really get what you buy. However, when it comes to integrated circuit design, you're not always sure what you get when you arrive, or when you get back the produced chip. Another issue is when it comes to integrated circuit design, you can only verify your design in the first step by simulation, because the chip needs to be produced, and that usually requires a long time. So this is the advantage of discrete circuits, because you can easily put it on a breadboard and go into the lab and do some measurements in a very short time. So on this slide, I want to show you how basically the chip design process itself works. First of all, you need a professional software. It's often used in industry, and it takes quite a long time to be able to work with this software. Then, shown here, you basically do the schematic entry, similar to discrete circuit design. For example, they have LT-SPICE. Then you do the simulation. After simulation, if you are happy with your results, you go into the layout. I will give you some examples on the next few slides. After that, if you have done the layout, you basically send your layout to the foundry, which produces your chip. And this production step usually takes 6 to 8 months, so quite a long time before you get back your chip. And after that, you only get a piece of a wafer, and it's not a chip. You have to put this wafer or this sliced die into a package, and then you can go to the lab and do some measurements. So quite a long time until you can go in the lab. So when it comes to analog design, you have to be aware of some certain qualifications. you have to know about semiconductors. You have to be confident with circuit design. You also have to know something about control theory, because when it comes to circuit designing, you must think of the stability of the circuit itself. And of course, you must know how to simulate the circuit. So here on the right-hand side is a short graph that shows the steps when it comes to designing a chip. So first of all, you have a specification, and from this specification, you would go in the design, do some simulations. If the simulations are okay, then, as I said before, you would do the layout. After the layout, there is an important step when it comes to integrated circuit design. You basically extract information from the chip layout, and then you do simulation again. If this you are fulfilled with the simulation results, you then send the chip into the production. And after that, as I already said, you do some packaging, and then in the end, lab measurement results. And if the results are good, you are fine, but that's not always the case. You have to start designing again the next chip. So I'd like to show you some examples of the major devices that are available when it comes to circuit design. So here, for example, on the right-hand side, you can see a layout of a simple transistor. So in this case, this resistor has a 12 kilo ohm. And as you can see, it's quite small with roughly 200 times 150 micrometers. However, when it comes to resistors, the absolute value, in this case 12 kilo ohm, varies with the process itself. So what does it mean? When you, for example, get 50 chips and you would measure this resistor, I would guess there is no resistor having this 12 kilo ohm. So there is a lot of variation. For example, there could be 11 kilo ohm, or maybe in the worst case, 9 kilo ohm. So you really have to worry about this accuracy. And therefore, you have to do a lot of simulations. And in this case, to model or to look at resistors, you have to do Monte Carlo simulations. The next important device, of course, is the transistor itself. So I would say it's the primary device when it comes to integrated circuit design. So on the right-hand side, you can see a layout of an NMOS transistor in this case. And when it comes to transistors, the main parameters that you can change on the chip is the width and length of the transistor. So in this case, the width is 2 micrometer as shown, and the length is 180 nanometers. So the length basically defines the process node. So in this case, it's a 180 nanometer process because it defines the minimum available length. And by varying the length and width of the device, you can basically set or define the gain of a single transistor, which should be, so it's denoted here in this equation. So when you vary the width and length of the transistor, you can then change the gain. This is the conductance of a transistor, which is the gain. So far, I have shown 2 major devices. And if you're kind of familiar with these devices, you know how to simulate circuit, you have done a layout, you would end up with something like this on the left-hand side. So what you can see here, for example, is the layout of the last test chip I have made. And from layout, you send this to production. And what you will get back is then this tiny device here on the right-hand side, positioned in the middle. This is the actual microchip. So in this case, for example, the chip is about 1.5 millimeter in length and width, and the length is about 1 millimeter. So really, really tiny chip. And as you can see, this chip is in a package, and the step which is required to connect the chip to the outside is called bonding. So when you're finished with the bonding, then you can put this chip on the PCB, and again, you go in the lab and do some measurements. So this was a short introduction into chip design itself. And now I would like to talk about how to extend the prior art when it comes to the integrated magnetometer frontends. So from the scientific point of view, it would be good to achieve a magnetic noise performance of 10 picotesla at 1 Hertz, very important, and to be able to measure magnetic field amplitudes up to 65 microtesla. And of course, it all should be very power efficient. So looking at this block diagram I showed you in the introduction, is that these parameters are mainly determined by the feedback circuit. Again, this feedback circuit consists of a digital to analog converter, some filtering, and a circuit to drive the feedback coil of the Fluxgate sensor. So this brings me to the next slide, how to drive the feedback coil of the sensor. On the right-hand side, you can see a very, very simple model of a Fluxgate sensor itself. So how does it work? If there's an external magnetic field present, that is then read out by the readout circuit, and then the feedback circuit must provide a particular current to cancel the ambient magnetic field. However, what is important, the magnitude of the required current to cancel a certain magnetic field amplitude is defined by the sensitivity of the feedback coil of the sensor in use. So thinking back of the requirements shown here on this slide, we can then basically calculate with this sensitivity of the sensor the required electrical specifications for the feedback circuit. So what does it mean in this case? The goal is to have a low noise performance of 3 nanoampere and the feedback current range of up to 9 milliampere. And as I said in the beginning of my introduction, Fluxgate magnetometers, of course, are basically a DC instrument and maybe work up to 500 Hertz. So, however, when it comes to the Fluxgate sensor, especially the feedback coil of the Fluxgate sensor itself, you have to be aware of voltage headroom constraints. What does it mean? For example, if you are putting 9 milliamps into the feedback coil of a Fluxgate sensor, it is possible that there is a voltage drop across this feedback coil, which can be, depending on the sensor in use, up to 1.4 volts. What does it mean? When you think of modern CMOS technology, the available supply voltages are quite low. For example, in the use process, the supply voltage is 1.8 volts or maybe 3.3 volts. So this is quite challenging on top of the usual circuit design stuff. Another issue is when it comes to extracting the sensor signal. As I told in the beginning, you have to read out the magnetic field information at the even harmonics of the excitation signal, which is then here at 2F0 or 4F0. However, looking at this graph on the right-hand side, you get some feed-through from the excitation circuit, which must be attenuated. And of course, you have to be able to interact with different available Fluxgate sensors. So the first building block of the feedback circuit is a digital to analog converter. Digital to analog converter, in short words, takes a digital input word and converts it into the analog domain. Here on the right-hand side, you can see a schematic of the analog output stage of a digital to analog converter. So how does it work? You can see here you have a set of defined current sources, and depending on the digital input word, the current sources are switched on and off to produce a particular output current. However, I have to say, when it comes to circuit design itself, you have to deal with noise. And when you consider the intended operating range of the Fluxgate magnetometer, which is from DC to a few hertz, you have to deal with flicker noise. So here on this slide, I would like to show you the analog stage of the digital to analog converter that have been designed. So on the right-hand side, you can see the current source itself, which was shown on the slide before, but as often required when it comes to analog to digital converters or digital to analog converters, you also need some reference current or reference voltage. So in this case, you need a reference current. And what's interesting about this design is that this design has been made configurable, as you can change the current source and reference. And by changing current source and reference is what you get is then called chopped current mirror. And by alternating this configuration, you get a certain phenomenon, because it shifts the flicker noise, which is when you think of the Fluxgate magnetometer frontend, which is in the bandwidth of interest, which shifts the flicker noise out of the signal band to a higher frequency. So by doing this, the noise performance is increased. So on this slide, I'd like to show you that the digital to analog converter, in this case, the analog stage of the digital to analog converter, needs some additional circuitry. Why? Because the particular output current of this D to A converter needs to be amplified to provide the required current to cancel the ambient magnetic field. This is typically done by a circuit called current-controlled current source, which is shown here on the right-hand side. So what does this circuit? It takes an input current and amplifies this input current by a defined gain, and then produces an amplified output current, which can then be put or sent to the feedback coil of the Fluxgate magnetometer. However, when it comes to current-controlled current sources, you have to be aware of the output impedance. What is the output impedance? In this case, the output impedance is here shown as a simple, or modeled as a simple resistor, ZO. And this value must be quite high, because when you think of the current dividing rule, there can be a case that the required current for the feedback coil is not flowing into the feedback coil of the current, but can also flow into the output impedance of the current source itself, and thereby limiting the accuracy and precision of the output current. So what I did then in my PhD thesis, I looked at recent literature and tried to somehow identify or classify the available controlled current sources. They can be especially defined in two groups. The first group are called here, in this case, current mode circuits. Current mode circuits basically work by using currents for signal processing. On the other hand, there are voltage mode circuits, they work a little bit different because they generate the feedback current in the feedback loop of an operational amplifier. So I don't go into detail of this specific current mode circuits or voltage mode circuits. I then tried to somehow classify the topologies on the slide before in terms of their performance parameters. And what is evident, or can you see here in this slide, is that the current mode circuits basically offer quite good power consumption and are easy to implement using CMOS technology. And why is that? Because current mode circuits basically use simple transistor structures. On the other hand, the voltage mode circuits, in this case, there is a circuit called Howland current source, which offers excellent performance when it comes to noise and linearity, for example. So I decided then to more or less look at this specific circuit, Howland current source, because it achieves the required parameters for the Fluxgate Magnetometer frontend. However, the Howland current source itself has a drawback. It has no current input. And when it comes to CMOS implementation, it can be quite challenging. So the Howland current source itself is shown here on the right-hand side. It consists of a single operational amplifier, which is shown here in the middle. And this circuitry uses both negative as well as positive feedback loops of the operational amplifier. So how does the circuit work? The input voltage is amplified, and then here this resistor R2B then turns this voltage back into an output current. This is basically denoted here in this equation below. When it comes to the Howland current source itself, there is a so-called balance condition. So what does this mean? Balance condition means that the negative feedback path and the positive feedback loop must have the same resistive value as shown here in this equation below. And why is this important? Because this balance condition must be fulfilled in order to have a correct operating principle of the Howland current source as shown here in this equation. However, as you see, this Howland current source is a single-ended circuit. What does it mean? There is only one single output. And one drawback of this topology is that you can only drive a limited amount of current into a certain load impedance. Remembering from the introduction, when it comes to CMOS technology, you have to deal with low supply voltages. And when you put a current into the feedback coil, there can be a voltage drop of several volts. And this would not be easy to implement with this kind of topology. So I came up with a fully differential realization, which is shown here on the right-hand side. It consists of two operational amplifiers. The first one, here on the left-hand side, is called a transimpedance amplifier. So what does this circuit? It takes the output current from our D to A converter, and this resistor then converts this current into a voltage. This voltage then is fed to a fully differential realization of a Howland current source. So it's basically the same operating principle as the normal Howland current source, but with one major feature. It can drive more current into the feedback coil of our Fluxgate sensor. because it has a fully differential output. So the drive capability is basically doubled. I analyzed this circuit as a whole when it comes to output impedance, noise, and other things. However, which I've shown on the slides before, when it comes to CMOS implementation, it can be challenging. Because when you do some implementation of this circuit on chip, you have to deal with mismatch. What is mismatch? Maybe if you remember, when you implement the resistor on chip, you will not always get the same value of this resistor. So I analyzed this circuit in terms of output impedance. So first of all, as the Howland current source requires balance condition to have a correct operation, you have to take the mismatch into account. Because when you remember the equation for the balance condition, and you then have, or you then put the problem with mismatch on this equation, there will be a deviation from the ideal value which is required for a correct operation. So I then did some calculations and ended up with a quite interesting result, is that the output impedance, which should be quite high for a current-controlled current source, is mainly determined by how good these two output current-defining resistors are matched. I then implemented the complete feedback circuit on chip, where the chip microphotograph is shown here on the right-hand side. So it consists basically of a digital part. Then we have here our current steering cells or current sources, followed by the transimpedance amplifier and the fully differential realization of the current source. So this chip achieved the required current output range, but is worse when it comes to the required noise performance. I also have to point out that this special implementation was awarded with the Best Paper Award. So as the noise performance was not achieved, I came up with a simple idea: just neglect the succeeding transimpedance amplifier, which converts the current into a voltage, and then the Howland current source, the voltage back into a current. So it would be easy just neglect this amplifying stage. What would be the advantage? Of course, a reduced power consumption, because you have one active device less, and the noise performance should be also better. I then came up with my proposed concept of a fully differential current amplifier. It basically relies on the Howland current source principle. So how does this circuit work, which is shown here on the right-hand side? It's simple. It takes the input current, and this resistor R2 converts this input current into a voltage. And then again, our current defining resistor converts this voltage back into an output current. However, if you then connect the feedback coil of the Fluxgate sensor, then the resistor R2A comes into action. Why? Because the resistor senses the output voltage, thereby generating a feedback current that restores the voltage drop across the resistor R2B that produces the specific required output current. So I also analyzed this complete circuit when it comes to output impedance, but I also analyzed it in terms of noise. And what I would like to show you here are mainly 2 points. The first one is the output impedance taking other effects or combined effects into account. And stability. So when it comes to the output impedance is not only limited by the resistor, by the matching of the resistors, as I have told earlier, but also is limited by the gain of the operational amplifier that is in use. So looking at this graph on the right-hand side, what does it mean? So for example, if you would like to have an output impedance here, ZO of, for example, 1 mega ohm, you would need a quite high open loop gain of the operational amplifier. So in this case, the operational amplifier would require a gain of something like 120 dB. The output impedance is also limited in certain bandwidth requirements, because there is also a feedback capacitor in the feedback loop of this fully differential current amplifier. This feedback capacitor is also required for stability. So there is an upper limit of this feedback capacitor, because you have to assure that the output impedance is always there in the required bandwidth requirements. Thinking back of the requirements from the Fluxgate magnetometer, you have to have a certain output impedance from DC to, for example, 500 Hertz. So the next topic I will just explain very briefly is stability. I also analyzed this circuit when it comes to stability, already taking the feedback coil of the Fluxgate sensor into account. So looking at this plot right here on the right-hand side, you can see two curves. The first one is the gray one. This is the magnitude plot of the output current if there is no feedback capacitor used. So what you can see here is that there is a peaking of this output current. What does it mean? The output current is oscillating quite strongly. The message is you have to use a feedback capacitor, because looking at this graph, what you can see here is that the peaking of the output current is reduced to a certain amount. However, I have to say you cannot make this feedback capacitor arbitrary high, because you have to fulfill the output requirements of the output impedance itself. So there is a certain trade-off in bandwidth of output impedance and stability of this current source. So here on this slide, I'd like to briefly show I not only analyzed circuits, I also built some circuits. And in this case, this is the operational amplifier, which is required for the current source. I would not go into detail because it's not the topic today here. I also implemented this complete circuit on chip together with the D2A converter, and again with the more or less improved version of or my proposed version of the current source. So this implementation basically achieves the required noise performance, and of course the current range is also maintained, and the power consumption is also quite good. So when it comes to the scientific part, I would say I have extended prior art controlled current sources, especially the voltage mode circuits. And when it comes to the Howland current source, I would conclude that this new circuit is then called a Howland current controlled current source and offers an current input, and I have shown how to implement this circuit on chip. So the next topic is the Fluxgate Magnetometer frontend proof of concept. So the designed or implemented feedback circuit was then produced, put in a package and on a test board. So here on the test board, you can see the package chip that contains the feedback circuit. However, as you can see on this test board, the other required circuits are realized externally using discrete components. And in front of this test board, you can see a Fluxgate sensor, and in this case, it was the LIN sensor. And the measurement of this proof of concept were then carried out here at the institute by my colleagues. And the achieved noise performance is quite good for the LEMI sensor, because here at 1 Hertz, the noise performance is at 22 picotesla. And with the LEMI sensor and the used feedback current range, the range of the maximum field amplitude in this case was 22.5 microtesla. However, I have to say that the noise performance is not only defined by the electronic circuitry, but also defined by the Fluxgate sensor in use. So when it comes to prior art space qualified frontends, in my opinion, we have increased the dynamic range and noise performance when it comes to integrated frontends. The next topic then would be how to extract the sensor signal. Basically, there are 2 options available to extract the sensor signal. First of all, the first thing would be to use digital circuits to basically do the extraction in the digital domain. But there is also one option available, and in this case it's called a lock-in amplifier. So briefly, how does a lock-in amplifier work? The magnetic field information, as said before, is stored at the even harmonics of the excitation frequency. So this circuit then amplifies this sensed voltage, filters it, and demodulates it back to the required DC component. And this is done by a mixer that requires, in this case, a phase shifted or phase correct signal of the even harmonics. So I also looked at how to improve lock-in amplifiers, because the prior art lock-in amplifiers basically lack in their filter performance. So I then came up with a new concept. I will not go into detail. I will just show you here the schematic. So how does it work? When you remember the photo or graph before, is that there is not only the even harmonics, but there are also the odd harmonics that have to be attenuated for a correct operation. And the benefit of my proposed lock-in amplifier is that the center frequency of the required filtering function can be tuned with the 2F0 frequency that is also required for demodulation. So looking here at this plot on the right-hand side, you can see the bandpass filter response for basically 3 different 2F0 frequencies. In this case, it was 10, 30, and 100 kilohertz. And as you can see, if there are the odd order harmonics, for example, there will be enough attenuation of these odd order harmonics. So I also implemented this concept on chip, which achieves quite a low power consumption in small area. But if you remember from the beginning of my talk, there can be the case that when you arrive or when you get back the chip and do the measurements, that you have to start designing again because some of your measurements didn't turn out quite well. This was the case considering this lock-in amplifier. So I just want to conclude my talk with the main research contributions. So in my opinion, I extended the performance of integrated front ends or Fluxgate Magnetometer front ends by doing an analysis, design and implementation of the required current amplifier for the feedback coil and of proposing a new concept for a lock-in amplifier. And in the end, you can see the last test chip that is currently under evaluation here at the Institute.
Oh, thank you very much, Max, to give us to bring this topic or break this topic down to even physicists can understand. So questions.
Yeah. I didn't really understand the working principle. So could you go back in the big one? You don't need to go back to explain how the two coils work essentially. So you have the excitation coil,
yes,
and the sensing coil. And why do you need the feedback to? Is it going to the sensing coil or to adding to the excitation?
It depends on the sensor in use, but in I would say in most of the sensors there is a sense coil and a pickup coil. And you need the pickup coil because you want to generate an opposing field to, in the next step, cancel this ambient magnetic field. So basically, it is a zero instrument. You generate a field within the Fluxgate sensor to compensate the external field.
And this is what, at the end, when you get zero, is what you record.
Yes.
The thing that you put in to cancel is what you record.
Yeah.
And another question on the ASIC design. So when you do a PCB like with normal components, you can have different layers and you can route the signal up and down and you can simply cross signal like this. On the silicon, can you also do this, or are you limited by just one layer of circuitry that you can?
When it comes to chip design, I think there are 40 to 60 layers available. And regarding your question, from the routing point of view, you have, depending on the process, of course, 4 to 6 metal layers that can be used to route between the individual devices. So you can go up and down, similar as on the PCB.
More questions? Then maybe from my side, if you skip to slide 30, I think we will go to the right?
Sure.
So you said that the capacitor is needed to stabilize this circuit or feedback coil, so to speak. And but in the beginning, you said you drive this coils with 10 kilohertz round, roughly?
Basically DC.
Ah, DC, okay. And so here we see then the AC.
Yes, yes,
AC. Yeah. Yeah.
Thank you. Very interesting. Another question. We have the full setup, including the sensors. Is it possible to have a calibration sequence from time to time in order to characterize the varying Fluxgate sensor parameters?
No, not yet.
Because otherwise you rely on external calibration sequences.
You're right. But I have to say, when you look, for example, at the last microphotograph of the test chip, so there is only basically the analog circuits. This chip would also require a digital FPGA that does the digital stuff, like, as you said, calibration. Yeah.
Okay, thanks.
Okay, got it.
So in your diagram, the feedback signal, it's always after, so you digitalize, then you do integration, and then you put it in the analog domain again. And my question would be, is it possible to have this feedback in the analog domain? So how not having the digitalization in between, and would you gain something out of it? I mean, I guess it's a bit what you said, the last part of your talk with the mixing. I'm just wondering why you need to digitalize and then put it back into analog.
Yeah, the digitalization is required because the scientists need the data.
Yes.
So you
Maybe I could help you if you
And you could still digitalize it, but it's not in part because when you put it in the analog again, you have noise from this.
And in principle, yes, but there are analog implementations of this feedback loop, but typically they have not that good noise features and not that good stability features in comparison to the digital ones.
Okay, so last question you answer.
What is the quality of the semiconductor material? Is it possible to improve the noise when you use a different procedure in the fabrication of the chip?
The noise performance not only depends on the use process, it depends mainly, or it also depends on the required voltage headroom that you have. So if you have bigger voltage headroom, then it would be possible to reduce this noise performance.
Okay.
Is that question in the chat room?
Not as user.
Not yet. No. Okay, so let's thank the speaker again. We will have next, I think, colloquium Thursday, if I'm right, and hope to see many of you there. Thanks for coming.